Welcome to how to migrate MySQL database into Kubernetes. Today we're going to do a demo. We're going to try to be quite interactive. You have a Q&A section in your Zoom. Throw any questions there, and at the end we'll do at least 15 minutes of questions. My name is Farhan. I'm a reliability engineer at StorageOS with a background on systems engineering. Paul is also with me today. So Paul, if you want to introduce yourself.
Hello guys, I'm Paul Sobey. I'm head of product for StorageOS, and I work with Fran in the reliability engineering group.
Great, thank you, Paul. By the way, everything we do today is going to be recorded. We're going to send a recording later on, and any links that we show. So don't worry too much about taking notes and everything. Who we are, StorageOS, probably most of you know us, but for the ones that don't, we are a company that are building a cloud-native software-defined storage engine for running containerized applications in production. So we are enabling production stateful workloads for Kubernetes environments. So let's start and let's get into it. Today we want to move from a MySQL server, let's say a big instance, whether it's a platform or infrastructure where you have active passive model, maybe with read replicas, or you're running an RDS server on Amazon or instance, to a different model where instead of having to take care of that service and having all the databases in one place, we're going to move that into an architecture that is based on microservices with all its pros and cons. We're going to try to discuss a bit of that later. So we're going to start with one server that has multiple databases, and we're going to migrate one database on a different instance of MySQL running as containers. To be able to do this, we're going to have a Kubernetes cluster, and we have StorageOS installed in it. StorageOS will give us the capacity to run this production workload, but today we're going to focus more on the database point of view. So let's start and let's have a look at what we have. Just for context, I'm going to use K instead of kubectl for everyone's speed and simplicity. I have a few nodes running, and I have specifically 6 worker nodes. Great. So StorageOS is installed using the StorageOS operator on those 6 worker nodes in the kube system. So I'm just going to list the pods specific for the StorageOS, and we have these 6 daemon set pods, which are the main StorageOS component, whether other components are also installed. So StorageOS takes that, the host where it's running, and it provides the capacity of that specific node to provision volumes. We have a service in that namespace as well that I'm port forwarding. So I'm going to access the StorageOS user interface on my local host machine. So let's go have a look at the StorageOS UI on my local host. So we have the 6 nodes. I know that you can see 7 because there are 7 nodes. One of them is only for etcd and pretty much a control plane that is not a worker. So 6 nodes here. Now, the other component that we have, or the other thing we have, is the MySQL Server. So we have a MySQL Server, as I said. With 10 databases. For simplicity, I'm doing ab 1, 2, 3 to 10. Keep in mind this, or try to think this of one database for each service of my application, whether you're a business company or you have an application that have different components, let's say a user service, while there is data service, or maybe an exports, or the CMS part of it, etc. So one for each, and this is what we will actually move into a containerized MySQL. Cool. So let's start. The first thing that we need is a MySQL running for every microservice. So I have one namespace in Kubernetes for each microservice. Now let's deploy a persistent volume claim and MySQL on every single one of them. I'm going to use this repository, which is public, is in GitHub. Any YAMLs I'm using today are available. Let's see, MySQL. So I have a few YAMLs. Let me create first the resources, and now I'm just going to show you. I'm going to iterate over all the namespaces. I highly, highly recommend that anything that I'm doing today, you do from a CI/CD server or pipeline that you have. I'm doing it by hand for show, so you can actually understand and see what's behind the scenes, but everything should be done in a CI/CD server, whether it's Jenkins or whatever you like to use, or even from a GitOps point of view. So now I just create these stateful sets. I create one stateful set for every namespace, and let's have a look at that specific name stateful set. Stateful set is a Kubernetes controller that will enforce that we have one instance of the application running, but not the same as a deployment. We will enforce that we have always the same pod or the same instance of the pod with the same name and with the same PVC, so the same data associated to it, and it will guarantee some constraints like mounts and unmounts for specific file systems and volumes, which is really important for stateful workloads. Another component here important, or another point, is that we're using standard MySQL. I use MySQL 8, just standard container for demo today. And we are mounting a volume into Barley MySQL where data is stored. Where is this volume coming from? The volume is coming from the claim template. The claim template is a way to associate one pod to its PVC, and the controller is handling this for us. So we just need to tell which storage class is using and the size of that database. I'm putting quite a small database for today. StorageOS implements also resize volume, so this is just for show, but also you can set up any size that you want here. So the StorageOS replicated storage class will use the StorageOS provisioner and provision that MySQL PVC with the StorageOS. So let's pick up one namespace, 3 for instance, pod. So we have the MySQL running and the persistent volume claim that is associated to it. Great. So you can see that we have 10 MySQL instances running in my cluster, and we're going to do the migration. So now we have an empty instances of MySQL. Let's go and start running the migration. How do we do this? Well, I'm going to connect that server towards, so those applications can access to it. They can do an import through IP, or actually we can do it with a DNS name, which is a bit more elegant. So I'm using external service. It's just a fancy way to make sure that whether an IP changes, we keep the same name on the service. So we are referencing an external IP of the cluster to one specific DNS name. It's actually quite elegant, in my opinion, that Kubernetes allows us to do this kind of decoupling. External, and we just need to create the service. Correct. Now, let's proceed with the import. How do we import that data? How do we do this migration? I'm just going to use a job. A job is another Kubernetes controller that will run at least one instance of this application. I just set it up to have only one execution of this pod, and it will run as a one-off job. It's a simple MySQL dump. If you're familiar with MySQL, you probably know that MySQL dump is blocking. So for production environments, be a bit careful with this. If you have big databases, again, you can decouple and have two jobs, one for importing and the other one for exporting and the other one for importing. Just be a bit careful with this because I have really small databases and it's just for show. I'm just doing that in one shot. Be a bit careful. Okay, what's important from this MySQL dump is the source and the destination. These are just environmental variables. And where these environmental variables are coming from is from configuration. So we're going to have one of these jobs for each namespace. And what's going to be different is the configuration that we are sending to that environmental variables that we are sending to the containers. So we are using a source for that external service that points to the IP of our MySQL instance, and the destination is namespace. So it's just pod name.service because the job will run in the same namespace, so we don't really need to reference it. Great, it's quite automatable, it's fairly easy, and the only thing we need to change on the fly is the app. So the database itself is called different, so we're gonna create the config maps and then alter this with a patch. Again, you can change this on a CI/CD. You can have templating, or maybe tools like Customize to the templates for you, etc. I'm gonna do it by hand, so you see actually what's going on instead of having some black magic around. Let's create for every namespace a config map. And let's apply a patch. The only thing that the patch will do will be iterating over the namespace and change the database for the right name, nothing else. So we apply the patch. Let's have a look to confirm, at least in the app that I am now, which is app 3. You can see that for app 3, we have the specific database. Instead of having app, we have another one. Great. Now, we have 10 instances of MySQL, and they have their own configuration. Great. Now, let's actually run the migration itself. Once again, I'm going to loop over the namespaces and create the job. There are different ways to do this, obviously, and you can find many more. Again, this is a CI/CD based kind of pipeline, but I'm just showing. So let's have a look actually at the pods. I'm using K9S because actually it's a pretty cool tool for real-time information. So we can see the MySQLs, and we will see now the populate. Let's say for app 3, it actually finished to see the pods, the jobs that the job triggers a pod, and that pod already finished. Let's have a look at any of them. For instance, app 3 is the one we were. So let's go and have a look at the logs of this container. And we can see simply the output of the verbose of the MySQL dump. Quite simple. An insert is a very small table, obviously. It finished, it completed. Great. Now we have already an application that has data on itself. So let's say to app 3, let's go in, and I'm gonna get a shell into the container itself. Well, awesome. So we have in app 3, database app 3. In app 2, we'll have app 2, app 10, we'll have app 10. So if we have the user microservice, in the user microservice, we could have the user database. Great. Let's see some data. For instance, just random data, nothing important. Just we have data in there that is being migrated from that main server. Awesome. Now, we just have done in a few minutes a migration just with a few YAMLs, maybe a click of a button for a Jenkins server. And we passed from a big server to multiple small servers. Why did we do this? Well, there are different reasons that we will talk about database as service later on. But keep in mind that now you can start tuning every single instance of MySQL for what's required. If you have an instance, for instance, or a microservice that is very intense on reads, maybe you want replication, and you can add read replicas for that specific MySQL. While another service requires low latency, we can work on a better latency based on collocation that, for instance, StorageOS can guarantee. Or we need other kind of scalability. So in this model, we are decoupling the needs of an application to the instance where it's running. So you can start tuning and setting up per application or per workload what is needed. Not to mention the blast radius, that if I lose or one of the applications start using all the resources of that database, the other databases get affected, or the other queries. So we are splitting a bit the problem. We're dividing and conquering. Obviously, it has a consequence that there is some overhead of running multiple MySQL instances instead of one, yet it's usually quite a small overhead. So what else we can do now that we have these running containers in Kubernetes? It's fairly simple. Now, what do we need for a production, from a production point of view? We can do something a bit interesting, and let's have a look at the StorageOS UI. So StorageOS on itself will show us per namespace the volumes that we have. So we were in NAP3 to keep with some consistency. And we can see that we have a primary volume in demo 3 while a replica in demo 7. So if we go to the volumes, let's have a look, we can see that we have the primary, so where the data is stored by StorageOS and where it's mounted, so where the pod is running, while we enforce one replica. And we did that with the storage class, enforcing a simple label, storageos.com/replicas equals 1, meaning 2 instances of the data in sync. Why I'm saying this? Because actually this is what is giving us, and by default, active passive model for our database. One node with data, the other node with data, always in sync. If I go to different application, let's go app 1, we will see the volumes. And we can see actually something similar. One replica, because it's enforced by the storage class, while the primary node is in the same node where the volume is attached. That is the best performance we will get because we are minimizing the latency mainly for reads. Writes will still have go through a network because of their application target, but it is still the lowest latency we can achieve while having synchronous replication. Great. Now let's go to app 1. We can see it is mounted on the same node, while the primary is in demo 6 and the second one is in node 1 or demo 1. So let's go to app 1. Let's change namespaces. We have the same as before. Now, let's start the pod somewhere else. So I'm coordinating the node and I'm deleting the pod. In this way, I will enforce that this pod cannot start in the same node. It has to start somewhere else. Why? Well, it's, in my opinion, a big requirement for any production workload in Kubernetes is that the container should be able to start anywhere in the cluster. We'll have performance differences, obviously. However, our data can be accessed from anywhere in the cluster. So the application is not tied to one specific node. It was starting before in node 6, now is in node 7, right? So we just started the database in a different node and it's just starting fine. Let's actually have a look. Just playing MySQL once again. And we have the database that we were having before. Everything is the same. It's just accessing the data from a different place. StorageOS is doing that under the hood for us. So if we go back to StorageOS, let's have a look. We can see that now they are in different nodes. Great. We can start from one place and we can move our containers anywhere. Why is this important? Well, data takes a long time to move, while containers start real fast anywhere. So we would have to move data and make the data follow, even if it's just network attachment volumes, it can take quite a long time. In this way, is almost instantaneous. The second bit is self-healing and automatic failover. Let's have a look at that. We're saying that the data of this specific application, this specific MySQL, is stored in demo 6, in this specific node. Let's go and shoot that node. Let's go and see what happens actually when that node becomes unavailable. So I have all the shells in here, and we're saying that in demo 6, we hold the data. Here we are. You can see I'm just gonna click reboot. So I'm just gonna put the node down. Node is down. Take a couple of seconds, obviously, to stop. And even though Kubernetes will not detect that fast enough, it's showing us ready, StorageOS has its own health checks. Because I stopped this, let's recreate the port forward to access once again. And let's have a look. Let me refresh because I just rebuilt the port forward. Great. We are still in app 1. You can see right away that the volume is in a different node. The primary volume is serving from a different node. So the data itself has been failed over the access. So let's have a look at the nodes and see the demo 6. Let me put this in order. We can see that demo 6 is actually marked as offline by StorageOS. No longer holds a primary volume, but where the replica was before in demo 1 is where the master is now. So we failed over the volume, and a new replica has been created in demo 5. Why? Because this is a declarative model. We want to enforce one copy of the data always in sync. So when there is none available, StorageOS automatically creates that for you. Let's have a look. Great. And because obviously there is a small amount of data, the sync is almost instantaneous. With 100 gigs, maybe we would see that now syncing. And actually, StorageOS has partial syncing, which means that if the first node comes back and it has more in sync data than this one, it will remove this one and resync the differences to the other one to avoid the amount of syncing of data that it was already on a different place, and it's healthy. Great. So we just failed over the volume. How did that happen? Actually, let's see what the MySQL itself saw. We were in app 1. Just remember, the application sees no restarts. And simply, we see the same files as before, same data. We are just accessing a device, at the device that StorageOS is providing, and under the hood is managing, while it's pointing to one node or another to access the data is completely irrelevant for the container itself, for the file system that MySQL is running. We have the same data as before because I imported actually all the databases had the same data to be able to show you that. So we have failed over the volume. How this happens? Well, StorageOS implements, as I said, synchronous replication. So every time that application writes, that write is sent to the replicas, and when everything is stored, we go back to the file system or the syscall returns successfully, saying that the write is done to the file system inside the application. In case of a node failure, the health checks of StorageOS self-detect that, fail over the primary volume almost automatically, and create a new replica because that was missing. So we have an active-passive model out of the hook for any stateful workload that you're using. Now, let's talk a bit about the model that we just see while implementing this migration. We pretty simply moved from one instance that was fairly big, or that can actually be big, and that is difficult to support, maintain, grow, or adapt, that it requires usually operational downtime while, for instance, we want to do a vertical scaling. So we want to make a bigger machine. That database usually has to stop, or we have to fail over an active-passive model, either using Peacemaker and all this kind of work. While now, we are just having the containerized benefits while we can run an active-passive and have high availability for our database. So when using this kind of model, we can start building databases as a service for our teams, for our products, for different microservices, for instance, and we achieve some decoupling across resources, security, etc. So what we've done today, we have shown something that I'm quite fond about the Kubernetes model, which is an application-centric storage provisioning. That looks pretty trivial because from a declarative point of view, we're asking that for that database, that application, we just want this amount of capacity. But think about it. Usually, you would have a traditional environment where you would have a host or a VM, you could plug some disks or remote disk or local disks, And from there, you could put an application or two or three that could write in there. Now, what we're doing is asking for capacity from an API point of view, from a declarative point of view, etc. We are asking storage for an application, not for a host. And that has quite a lot of implications that makes very reproducible. And coming to the second point, makes the declarative and reproducible of this solution very easy to start and stop, and to start in different clusters quite easily, or to reproduce even when testing on CI/CD pipelines and environments. As I mentioned before, we have quite a good workload, a specific database tuning. If you want, you can, because now there is no one solution for all. Now we can tune for writes, we can tune for reads. Maybe some microservices are more key value store, while others have a lot of relations and a lot of joins and need quite a different set of resources. We can specify specifically for that. Instead of having one database that has to do everything, we have a farm of nodes, and we can tune specifically by just passing configuration. Of course, for high performance, more tuning can be done, and we can specify some set of machines that are specific for that with faster disks, etc. But is a set of machines that we can choose from a declarative point of view once again. We have seen that we can do database endpoint abstraction. So when we have to access databases, we can just leverage the Kubernetes networking and DNS model, which is actually quite comfortable to use, quite easy, and solves many problems. And we can easily horizontal scale our platform and our databases. We need more machines. StorageOS is running as a daemon set, so the new machine will see StorageOS, will have more capacity. The orchestrator sees the new node. You can provision applications there, etc., etc. So easily we can put more microservices without having to look too much at the size of the database itself. And in fact, most of the storage providers or provisioners support resize of the volume. StorageOS supports that as well. So in case that one PVC is not big enough, simply you can resize it. On the other hand, it's very important to keep in mind that very often disks or in cloud providers or network disk providers such as EBS or Google Cloud Disks are define their performance based on the size. If you have multiple databases, you may not want exactly to have to provision a big disk to have a small amount of data just to guarantee some bandwidth and IOPS. With this model and using at least software-defined storage for this specific use case, we get rid of this because the IOPS are coming to one EBS instead of having many in the same node. I'm saying EBS as I could say any other block storage device based on cloud environments. So to finish a bit with this and try to be concise, you can see the docs of StorageOS. In there, we have also a use cases section that points to the GitHub repository I used today. We have a self-evaluation guide, which is a step-by-step through installation of the StorageOS, how to benchmark things, how to test functionality, etc. We are very active on Slack as well, so we are always there. So if you have any questions or anything you want to know about the community, you can join our Slack. And as well, you can just email us at info@storageos.com. Now, we're going to pass to the Q&A and have a bit of questions. Hopefully, Paul will help me with this. So welcome back, Paul, to the call.
Thank you very much, Farhan. Yes, we do have some questions. Just a reminder, guys, while we work through these, please do post any additional questions into the chat using the Q&A button at the bottom, and we'll do our best to get through them. Any that we don't get to today, we'll take some notes and we'll get back to you via email or some other offline resource. Okay, so beginning with a question from James. The demo shows MySQL running in Kubernetes. Are StorageOS customers really doing this with production workloads?
Definitely, yeah. That's actually a good question. Very often people think that Kubernetes is a fairly new thing. Actually, it's been around for a while. While we have seen a lot of stateless applications, we see quite a lot of more and more people moving to production. We see clusters that are 50, 60, 100 nodes easily running this sort of workloads. and treating databases without a problem as what they call cattle instead of pets. So just treating databases as machines, or quite from an automated point of view. We have quite a few clients ourselves, and also there is other people in the market using storage providers. So today, running production workloads from stateful applications such as Elasticsearch, Kafka, Jenkins itself, or any Jira servers, etc., is fairly simple, and we see people in production all the time with this, definitely.
Brilliant, thank you. And now we have a question from Aman. What are the advantages of running stateful applications within Kubernetes as opposed to outside?
Well, one thing that is clear that Kubernetes brings to the table is the fact that we can port the applications and start them real fast anywhere. So we don't have to worry too much about dependencies. All the containerization comes into play. So we're just leveraging that with other kind of applications. Stateless applications usually are really good at for scalability, and usually they keep state. What happens is that state is usually delegated to other applications. What we are enabling with this kind of model and having a storage system that is reliable for production workloads is the capacity to move those workloads to Kubernetes and take advantage of this model. It's very declarative, it's fairly to provision, it's fairly easy to have multiple environments where you're running the same thing. So reproducibility and construction is very easy from us. Sorry, I'm just messing around too much, I apologize. I would say we are taking advantage of the Kubernetes and containerization features on other applications. We no longer have to be hitting one specific server for one thing, another server for another thing. We have a farm, and we have a pretty good controller that handles where things are running.
That's great, thank you. And now a question from Sophie. Is it best practice to run MySQL with StorageOS using replicated volumes?
Yeah, that's actually a good question. I would say that that depends. For production environments, I would highly recommend use at least one replica. Many applications and many stateful applications implement their own replication. MySQL, for instance, have read replicas. They are not incompatible. When you have read replicas, for instance, you have a synchronous replication based on a transaction log. That can be slow, or that can add load to the master, or the primary where you write to the MySQL database. And that's not a bad thing. It's good because you improve throughput. However, what happens if that service goes down? You have to manually promote a read replica that maybe is not in sync. You have at 3 a.m. in the morning a call, which is not really great to have, and you have to fail over a database, while having StorageOS replication is giving you that by default. You don't have to do anything, you just self-heal. While other kind of applications, like for instance, Kafka, have a different set of, or a different way of replicating, where you can have the same message sent to 3 different brokers. Maybe you don't want to enable replication for StorageOS there and leave Kafka doing some of that, because you can lose messages. Let's say you have some sort of messages that are not, that can be lost. Yeah, don't use replication. If you lose a node, no big deal. You can start from somewhere else, and you have lower latency as well for performance. So I would say that having replication enabled by default is a good practice, but every use case is different, and you should see for your specific use case what suits you better.
That's brilliant, thank you. Do keep the questions coming, guys. Anything connected to running MySQL within Kubernetes on StorageOS is fair game here. One question from Steve. How should I back up MySQL databases within Kubernetes?
Kubernetes itself have different tools for backing up volumes. For instance, Velero is a CNCF project. We can use Restic in addition to it, that will go and not only the PVCs, but also the resources, the YAMLs, the namespaces, the pod, the deployments are going to be backed up on an object store. And we can use Restic alongside Velero to do the store of the data. That even Velero and Restic allow us to do file system freeze, etc. Sometimes is better to use a tool specific for that database. For instance, if you have a Cassandra where it has different parts of the data set and you just run a snapshot of a specific file system, not only is maybe it's not in sync and the data is not flushed, but it's actually meaningless without the rest of the data set. So using a tool for the specific database on stateful workloads, that is quite often the case, is better whether you're in Kubernetes or not. For instance, if you have Elasticsearch, you can configure Elasticsearch repository on an object store like S3, for instance, on Amazon, and keep the backups there, no problem. So there are two models. Again, what fits you best is depending on your team, the size of your systems team, etc. There are different options. MySQL DOM, as I showed today, is a completely good option if you have quite a setup on your automation that you can set cron jobs and MySQL DOMs. Fairly easy and actually fairly powerful as well. So two options. Choose the one that suits you best.
As in all things engineering, it depends is the maximum.
Exactly.
Brilliant, thank you. We've got a question from Maggot. I'm gonna paraphrase this question slightly. What are the minimum requirements for StorageOS to run on nodes? So sort of compute and memory requirements, that sort of thing.
So StorageOS made a big effort, or we as a company made a big effort to be compatible almost anywhere. So whether you're running cloud environments or you run on bare metal, the only thing that we need is a few kernel modules that are found in almost any distribution, such as Ubuntu, Red Hat, CentOS, or Debian, etc. Those are listed in the prerequisites. We have an init container when the daemon set starts that will enable them. And if those are not met, the daemon set will not start. So that is a pre-flight check that StorageOS that's on itself. Usually those kernel modules are available by default in most of the images. Maybe for some Ubuntu's, I think Ubuntu 18, you need to add the Linux image extra package instead of only the kernel package, because the kernel modules are just there. And after that, it's actually fairly trivial to install. We don't support currently Minikube because it doesn't have those kernel modules, but anything that is an Ubuntu, a Debian, CentOS will run. I can see in the Q&A saying, oh, I started this and I cannot make it work. Is just ping us on Slack, and in there, we will just have a look, ask you, okay, show me the pods, show me your configuration, show me how you install etcd, for instance, and more than happy, our team will jump in and help you troubleshoot exactly what's going on. StorageOS is quite low footprint. So if we have a lot of resources to be, a lot of IO, of course we will need more resources, but in general, we try to minimize the amount of resources we take from the applications, because we are running where the applications are running, and we want to give the machines the usability that they are meant for, their business cases that are meant for. So we try to don't consume too much, and if we can free memory, we free memory, etc. So usually 4 gigs of RAM, 1 CPU for StorageOS is more than enough. For 4 gigs of RAM, I mean, for the whole machine is, I would say, a minimum requirement, and is quite often finding this kind of machines. Bigger machines better, yeah, 100%. But yeah, we try to have a low footprint.
That's great, thank you. And that concludes our questions. We do have 1 or 2 others, guys, that are not necessarily sort of MySQL specific. So I've taken some notes while this presentation was going on. We will get back to you offline. But for now, that concludes the webinar. And I want to thank you very much, all of you, for your attention, and look forward to seeing you next time.
Thank you, everyone.